Okay, so lecture 11, cannons. Well, really, it's 2D kinematic problems, specifically 2D projectile motion kinematic problems. And so what are the kinematic equations in 2 dimensions? Well, the ones that I want you to know, right, we're going to split this up into 2 components, x and y. So in the x direction, which I'll assume is horizontal, which is the direction that will have no acceleration at all, whereas the y direction will be the direction where we have this downward acceleration due to gravity. So in the x direction, we have no acceleration, so the velocity in the x direction as a function of time is simply a constant. So it doesn't even have a time dependence functionally, and it will be equal to whatever the initial velocity in the x direction is, a constant. The value of x as a function of time will be equal to the initial x position plus v naught x times the time. It's pretty simple. Now the y component is a little bit different. So the y component will have an acceleration. So the acceleration, well, actually I'll write this up here. A sub x equals 0, so that means there's no acceleration in the x direction. Whereas for y, we have a sub y will have equal to minus g. So whether you want to use 32 feet per second, or 10 meters per second, we'll use both in different circumstances, but we'll assume that our y-axis is always going up, and so this will always be in the negative direction, and g is one of those 2 constant numbers. Now the velocity in the y direction will be equal to the initial velocity in the y direction minus g times t. So minus whatever component we get from the acceleration. This is just like the 1D problems that we've done before. The position function, y, that's how high up we are on the y-axis, will be equal to y naught plus v naught y times t. So just like it was for x, but we have the acceleration component acting in the opposite direction, in the downward direction, minus 1/2 gt squared. And this is completely analogous to the 1D problems that we did for projectile motion before. Okay, so to really see how to use these, let's just do a simple problem, and we'll call this a cannon problem. Okay, and so what I'll do is I'll have my cannon, and I'm not going to worry about the height above the ground of the cannon itself. We'll figure that maybe it's submerged below the ground a little bit if you want, but that it launches with some angle, and this angle theta we'll specify, and with some velocity, and I'll write down a magnitude for the velocity vector here in this direction. And so what happens is we're going to get a projectile motion that looks something like this. I will demonstrate shortly that this actually is a parabola, but for now I think we're all familiar with the general idea of that from experimental observations. So when working a problem like this, typically you want to find out something like, well, how far does it go, right? What is this displacement in the x direction? In the y direction, right, it's really the same as this. So let me just draw a little illustration to point out something very important. I could try and do it manually here first. If I were to, let's see, I've done this before, but how did it, oh, here's how I do it. I'm going to flick this vertically and drop this simultaneously. And if you listen carefully, you'll hear that they hit the ground at the same time. There's a little bit of a double bounce there, but maybe we'll do it one more time. Try to get it nice and level. So, what does that mean exactly? Well, that means that if I have a ball which is kind of kicked over the side like this, and then I have another ball that's simply dropped at the same time, what we'll find is the y position of the drop ball is exactly the same as the y position of the thrown ball, provided I don't throw it with an upward angle, or I don't give it any, initial velocity in the downward direction or the upward direction. If it's a perfect, push in the horizontal, then this will work out exactly the same. So what does that mean exactly? So if I had a rifle and I was firing it perfectly level to the ground, and let's ignore the curvature of the earth, how long is it going to take for the bullet to hit the ground? Now, most people think, oh, maybe it's a few seconds or something like that. And it's just simply not the case. This is exactly how long it takes to hit the ground. If you listen, you'll hear when it hits the ground. So I fire. That's how long it takes to hit the ground. As long as it takes for you to drop a pen from the same altitude as the muzzle of the rifle to the ground, that's how long it takes for the bullet to hit the ground. Because these two directions, the X and Y directions, are completely independent. So how do we solve problems like this? Well, how do we figure out how far it's going to go? Obviously, we want to know what X is. And we can let X not be 0. And so that means that X of t is equal to V naught X times the time. Well, what is V naught X? Well, what we can do here to show that this is actually a parabola is I'm going to replace this with some range. Oh, I'm sorry, I said that wrong. I'm going to solve for time here so that I get that t is equal to x over v naught x. And I'm going to take that time value and I'm going to substitute it into the equation for y. And so instead of y as a function of t, I'm going to get y as a function of x. Because wherever I see a t, I'm going to call y naught 0, by the way, v naught y times t, but not t. I replace t with x over v naught x. So now I have the ratio of v naught y and v naught x. And then minus 1/2 g times t squared. Well, t squared is x squared over v naught x squared. So I'm going to write this as 1 over 2 v naught x squared. And I'll put the g up here in the numerator times x squared. And so if you look at that, this is the form of a parabola. So this is the x direction, this is the y direction. So this tells us that what we're looking at when we see a projectile trajectory is the shape of a parabola. Now let's put in some actual numbers and see what this range would be. So let's assume that the muzzle velocity of the cannon, this is the magnitude, is equal to 1,000 meters per second. It's about what you get in a standard long rifle. And the angle, let's use one of the angles that we've used already. Maybe we'll use 60 degrees. So to get the range, we want to know what x is at the time in which it hits the ground. So we have to find that time. Once we've found that time, we can simply substitute it into v naught x times t, which is going to be equal to 1,000 times the x component will be the adjacent, so we'll use the cosine. The cosine of 60 degrees, which is going to be 1 over 2. So that's going to be equal to 500. Terrible 0, 500. Times the time. Times the time. Forgot to put a t there. So 500 times the time. Now, we need to know what the time is. Well, how do we figure out what the time is? And this is what you have to do in physics. You have to think about the problem and try to find a way to find the answer. So to find this time, it's the time it hits the ground. Well, how do we figure that out? We can't just set y equals 0 and say when does it hit the ground. Maybe instead we could do something like this. We could say, well, when is the velocity equal to 0? That could be useful. Well, the velocity is equal to 0 at the top of its trajectory, right? That's the apex. So when it reaches the top of the trajectory, the velocity in the y direction is 0. So what is that time? This is the location here, right? Well, this occurs, so v sub y equals 0, which is equal to v naught y minus gt. Well, v naught y is going to be, that says that 0 equals 1,000 times the sine of 60 degrees, minus g times t. Well, 1,000 times the sine of 60 degrees. The sine of 60 degrees is the square root of 3 over 2, so this is going to be 500 times the square root of 3. G, since we did meters per second, we'll use 10 meters per second for gravity. So that'll be minus 10 times t, and that's equal to 0. We can simply solve for t at this point. Doing so, we'll get that t is equal to 50 square root of 3. Just a little algebra there. I can now substitute that back in here and get my displacement. I'll write it like this. So x at the time 50 square root of 3 seconds is equal to 500 times 50 square root of 3. 5 times 5 is 25, so this should be 25,000 times the square root of 3, And the units, of course, will be meters. So it's about 25 kilometers, 25 square root of 3 kilometers. So somewhere around 50 kilometers. All right. So we'll stop here and pick up in the next one.